Thank you for joining us today. Today is Friday, the 29th of September. This is CSC241 Computer Architecture. What we're going to do today in our Friday hands-on session is to walk through the steps you'll need to perform in order to complete your custom logic gate build. And if you have your logic gate build ready and you go into tools and you open up your hardware simulator, notice I ran as administrator there just to make sure I'd have fewer problems. You have the ability to include or open specific logic gates. And one of the cool things that you can do is look at the pre-built logic gates to see how those are framed, see how the HDL works. HDL is a text file. So if we look at the built-in chips and we look at the, let's say the AND HDL, this is actually a plain text file, and I can open it with Notepad. I'm always going to use Notepad to open it. Can everybody see my screen?
Yeah.
Yes.
Okay. Now, some of you have 2 inputs, some of you have 3 inputs. And what you're going to want to do is you're going to save as, and you're going to say, my gate. I'm just using this as an example. Everybody with me? mygate.hdl. And can everybody see this right here?
Yeah.
Yes.
Does that match the name of the HDL file? If I'm doing something custom and I want to call it my gate, it says file name. Is that the file name I just created? It's not a trick question. The file name I just created is what?
My gate.
My gate. Does that reflect my gate?
No.
No. So I'm going to change it to my gate. Does everybody see what I just did there? That's really important. Now, if I create a custom gate, is that a gate that's created by Nissan and Shakam, MIT Press? Or is that created by Professor T. Kentop? And I'll put the date today, 29 September 2023. Everybody see what I did there? Hello, hello.
Yes.
Yeah, there's one more thing too. See that? That's a reference to what? And that's the original name of the HDL file and the gate. I'm going to put my gate here. But there's one more place I have to put it. Right here. If I do not have, let's see, there's a space after the name, and then there's curly brackets, left curly brackets. Remember that. So this is very specific. My gate and a space. Now, if those changes are not made, when I attempt to load and run this thing, I'll get an error that says, hey, the file name doesn't match, blah, 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 blah. You'll get this gibberish, right? But if I save this, and I save it as mygate.hdl, says, do I want to replace it? Yes, okay. So now I can go here and I can load a chip, a built-in chip that I created, my gate. And what I see now in the screen, does everybody get where I'm going with this? See my name? See the custom name? The custom logical statement and the custom chip name. They all match. And I don't have any errors on my screen, correct? Now we know that this is an and. We took the and HDL and we modified it so that we could claim it as our own. And you're going to do more when you combine the chips, you're going to pull them together. But I want to check to see that I want to see if this actually behaves like an and. So I borrowed an and, I put my name on it. I'm going to do more with it. But for now, I want to make sure it's working right. So in what circumstances does an and generate a 1 with 2 inputs?
When both are one.
When both are 1. So I could, what you're saying is I could double click here, highlight this value, change it to a 1, hit enter. I've changed the value input for 1. But if I leave B 0, it should generate what out here on the out pins? So let's run it. I'm going to run it. See, I double arrow to the right, I run it. And the grayed value becomes a solid value. Did everybody see what happened there? It was grayed out and now it's solid. I have an out. Now watch what happens if I do this and put both chips, both inputs, 1. I run it again. What should happen to the grayed out 0 here? If this is functioning correctly.
You should open.
Should turn to a 1 is correct. So here we go. Now, why is this important? You are about to put your own HDL statements in down here, and I'm going to have time today and time tomorrow to do that with you, to show you examples, to walk through that. But before you can, you have to do the other intermediate steps. This is actually the last step and the last part that you complete to log full credit for your solution. Let's say that again. This is the end, not the beginning, okay? But I want you to get a glimpse of how and what you're going to do when you're at that final stage, because people get through the rest of the process, then they get excited, the deadline's coming up, and then they rush, and then lo and behold, we have an issue. Everybody's seeing that? Okay, good. All right, so what we want to do now is go back into our solution. You take the drawing that you completed for 2.1. Now, what happens if your drawing was more complex and you'd like to just take something simpler? This is your opportunity to scale it down a little bit and try something simpler. I would recommend that you do that if you were one of those who were ambitious for your first submission of this solution. If everything works like it should and you have a successful submission and you log full credit, then when you get it back and you're like, yay, I got full credit, then come back again, add the other logic gates to what you've already built, see? And then submit again for additional credit. So it's kind of like putting training wheels on that motorcycle because you've never been on a bike or a motorcycle in these terms, right? What we don't want is for people to crash without a helmet and run screaming from the room because they can't get their creation to work and they throw up their hands and they run screaming from the room. And this happens every year. People get very discouraged. They're like, maybe I'm not cut out for this. I'm like, no, that's not it. It's a process. The first step is to take the drawing and then to create your truth table. We need to see everybody build a truth table right here, right now. And then when the truth table is done, we do the canonicals. And here's why the canonicals are important. This part right here, this statement from here to here is a comment. And your canonical is going to help you write this piece. So if we had a canonical of an and, it would say, and let's just open up our HDL again, right? So I'm going to go back into my NAND to Tetris. I'll go into tools, built-in chips. I'll go back into here. If I had a canonical that represented what an AND does with 2 inputs, and the inputs are A and B, the canonical would tell me only when A and B are both 1, would I get a 1 for an output? And that's language. I just stated that in language based on a canonical that would be A, B, no ticks. Everybody knows what I mean by that, right? A, B, no ticks. So this logic statement can be derived from the canonical. So let's recap. I have a drawing. From the drawing comes, I have a drawing. From the drawing comes the truth table. From the truth table comes the canonical. From the canonical, we derive the logical statement. Then we go back to the diagram and we get into this part of the build where we flesh out. Now, for those of you that have 3 inputs, you'd say, if your inputs were M, N, and O, you would say input M, comma, N, comma, O. Out would be out, right? And then you'd have other stuff down here for this part of it. So I will show and share a version of this at the end of the class so you can see what it looks like. But my purpose today is to make sure that people have good truth tables and good canonicals, and they can do this statement. Because if you don't get to the other part, if you don't get that done first, you're not going to get this part down here, okay? Are there any questions? So I'm going to stop recording. But what we'll do is we can share the screen. If some of you already have your truth tables, or you're willing to start your truth tables, and you'd show us your diagram, we can build the truth table together in class. I can work one-on-one with you, or we can do it collaboratively as a class, right? Is everyone okay if we do it together at first? Or would everyone just want to work on their own? And first of all, is there anyone who has their truth table completed already? Okay. So Mr. Flynn has his truth table completed. Mr. Flynn, would you be willing to show your diagram and your truth table? Show and share from the screen. Would you be willing to volunteer? For additional credit.
Sure, but I have to send the diagram to the computer.
Okay, so he's going to send the diagram to his computer, but he has the truth table built already. Has anyone else taken their diagram and created their truth table? Everyone knows where to get the templates for the truth table, correct? You go here into references, resources, templates. This is where you go. If you have an extra logic gate, like a NOT that it's a barred input, you're going to want, however many inputs you have is what you're going to use, but you may want to have extra columns or have extra information in the column. We've demonstrated that in class already. So each of you can take one of these 2 inputs. I don't think we have anybody that has a 4-input logic gate yet. But by the next module, we will have someone with a 4-input logic gate, a 4-bit logic gate, right? And then what comes next? 8 bits, 16 bits, 32. Everybody's heard of 64-bit processors, right? Can you imagine the truth table for a 64-bit processor? Yeah, we're not gonna freak you out about that. But if there were a 64 input and, what's one thing you could say for certain about how the output becomes 1? All 64.
All of them have to be 1?
All of the inputs have to be 1. Yes, thank you. Was that Milrain that?
Yeah, that was me.
I'm sorry, who?
Yeah, that was me, Mill Rain. Yeah.
Milrain, yeah. So all 64 inputs would have to be a 1 in order for the output to be a 1. And if any one of those 64 were 0, it would be a 0. How about the OR? If I had a 64 input OR, how many 1s would it take to flip it, the output to 1?
1.
Only 1. And that's a massive truth table. But I don't need to build the whole truth table for that, because I understand intuitively how and operates and how or operates. I also know what a not does. So for those of you that have been a little concerned because you're like, I don't know, this class, I mean, this is different. This is so different. If you can say and understand, okay, I get the whole and has to, everything has to be a 1 for the output to be 1, no matter how many inputs you have. Oh, just one of the inputs could be a 1 for an or, and my output would be a 1. If you know that much and you know that a not flips whatever's put in, then you have what it takes to finish this first solution, okay? So let me assure that. We're gonna do it together, and I don't want anybody crashing into the bushes without the training wheels. Is anyone else willing to share a diagram or a truth table? Okay, so what we're gonna do here is Eric is gonna share his screen. He's gonna show his diagram. We're gonna walk through the truth table. From there, we're gonna derive the canonicals and the logical expression, okay? At that point, we'll ask if anybody else is ready to do it because we want everybody in the same place. Then on Monday, I'm going to show everyone how we step together into the HDL environment to finish the process. So everybody crosses the finish line together. Okay? That's the goal. We want as many people across the finish line to have a successful solution together. We got to walk through these first steps. These are the tools for the preps that you use for a solution. And this is what they do in industry when they're getting ready. Now, with some variations, of course, okay? Local variations, local requirements notwithstanding. All right. All right. So what we see here is C, H, and O. And what we have here on the truth table is C, H, and O. And we have added columns, okay? And here's the cool part. So Eric understands intuitively that he has an and he has to resolve those inputs. He has 3 inputs total, so he has to have 2 cubed, or he has to have 8 entries. He has 1, 2, 3, 4, 5, 6, 7, 8 rows. He's chosen to put the 0s and 1s on the O input, then put the 0s, the alternating 0, 0, 1, 1, 0, 0, 1, 1 on the C, and the 0, 1, 0, 1, 0, 1, 0, 1 on the H. So he's chosen to arrange each of those columns. He's got all of these together. So basically all of the possibilities are represented by the truth table. There is one catch to this approach. If there's a problem rendering this later, it may be a little challenging to find out where things went wrong. What we want to make sure is that we have a 0, 0, 1. So we have a 0, 0, 0, we have a 0, 0, 1, we have a 0, 1, 0, we have a 0, 1, 1. Do we have a 0, 1, 1? We have a 0, 1, 1 down here. Okay. All right. So as we progress through the binary numbers from 0 to 8, from our first module, we know how that progresses. 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, right? We know that process. What's been done here may be better suited for the diagram. So this adaptation is completely authentic and completely valid. But if you're going to do that and you're going to have a truth table that deviates from the template, you just want to make sure that you have all the bases covered in the truth table and the combinations. Does everybody understand what I'm saying? So the first entry is all 0s, the last entry is all 1s. Let's finish the process to make sure we have everything. Do we have a 1 0 0 0, or I mean a 1 0 0? We have a 1 0 0. No, that's 4. Do we have a 1 0 1? We've already checked. That's 1 0 1 down here. Do we have a 1 1 0? We just found that one. 1 1 0. Do we have a 1 1 1? Yeah, we have a 1 1 1. So we have all the possible combinations of inputs. And just remember that in one column, half of them are zeros, half are ones. Then we alternate 0 0 1 1 0 0 1 1, and then 0 1 0 1 0 1. Now, the advantage of doing it this way is that what the intermediate step here is very clean. So that's another thing that Eric did by intention, and it's an appropriate and acceptable adaptation, and people do this in industry all the time. So Eric's already ahead of the curve, and he's thinking ahead of the curve. We just want those of you who are trying to track with the, okay, here's a 3-input template, why does this look different? Are there any questions about the presentation of the table and how it is equivalent to the template in Blackboard? Okay, let's continue and let's AND the input combinations between C and AND. Let's just check. If I have a 0 and a 0, the output is 0. If I have a 0 and a 1, it's 0. If I have a 1 and a 0, it's 0. If I have a 1 and a 1, it's 1. If I have a 0 and a 0, it's 0. If I have a 0 and a 1, it's 0. If I have a 1 and a 0, it's 0. And if I have a 1 and a 1, it's 0. I mean, it's 1. Is this column with the AND correct? Yes or no?
Yes.
Yeah,
It is correct. Thank you. Good job. Okay, that's usually the first hurdle when you have more than one. Now, we want to combine the OR. We want to take the output from this, the AND, and we want to feed it into the top input of the OR. But then we also have to flip the input of the O. And again, Eric's choice of table layout, as long as he has 8 rows, has strong advantages because he has the O inputs and then he's flipping them. And see how he's used the color coding. So now he's going to use OR between this column and this column. So let's walk through this. If the output of C and H is 0, and this is 1, and it's an OR that's doing this, what's the output? 1, because this output, this input is 1, all right? What about this next one?
One.
You can follow down, right? As long as there's a 1 in the mix between the what do we call that? Orange column, tan column, beige column. If you have a 1 anywhere in the beige columns, you have a 1 on this side. Does everybody see how we get that with an OR? Does everyone understand how we get that with an OR? Yes? No?
Yes.
Okay. All right. So, all right, hang on a sec. There we go. All right, so let's continue. He flipped the input on the O. That's what this column is. Down here, we have a 0 and a 0, a 0 and a 0, a 0 and a 0. That's why he has outputs 0 and 0. And then a 1 and a 0, so the output is 1. Does everybody understand how the output of the OR, the final output, is rendered as shown? Does everybody understand how we got 5 1s and 3 0s?
Yep.
Yes.
Okay, now let's assist Mr. Flynn with his canonicals. Which case makes the most sense for his output? should we do standard canonicals that represents each case where the output is a 1? Or would there be less work and it would be more efficient to represent each case where the output is a 0? A reverse canonical.
Yeah, the reverse canonical.
The reverse canonical would be correct. Now remember, when you're stating the reverse canonical or the standard canonical, either case, it's the original input, not the knotted input, okay? What am I saying? It's the original input before the knot. It's the original input before the and. It's all the original inputs when you're stating this. So there are 3 cases. The 5th, 6th, and 7th, let's look at each of the original inputs. What's the first case? So is C, when we're stating that first expression, it's a reverse canonical. What's the value of C?
0. So
Okay.
C.
And H is 0 and O is 1. So what do we do with the letters? Do we leave them unticked? Which ones do we tick?
C and H.
C and H are ticked. So it's C tick, H tick, O. Eric, there you go. He's got it. Okay, hit enter so we can go down to the next one. All right. Would anyone volunteer to take the next case?
C tick, H, and O.
C tick H O is correct. Thank you much. Does everybody understand where we got C tick and why we have H and O plain? Okay, and then, all right, last case. Someone else, please. C H and O.
C H tick O.
Perfect. Thank you. C H tick O. Now, here's the beautiful part of logic. Look at those 3. And this next question, I want to take quality time. So everybody just stand up and take a short break. Okay? Let's just everybody take, because I don't want anybody to miss this. I do not want anyone to miss this. And Eric, if you don't mind, zoom in on that sheet so that is really large, and then open up a notepad. Okay? Okay. Everybody take a stretch break there, 30 seconds, okay? Question. For each of the inputs, is there a case where one of the inputs has the same value all the time?
Yes.
Please explain. You're correct.
Yeah, the O.
It's the O. The O always has a 1. Everybody see that? Okay, so does everybody remember the logic statement in HDL? The logic statement?
The comment.
Yeah, the comment. Okay, Eric, for the sake of walking through this, would you mind opening up the AND HDL inside the built-in tools where your NAND to Tetris is, okay? Yeah, that's good. It's perfect. Tools, perfect. Built-in chips, perfect. Right-click and open with. You want to click on it. Yeah, you want to select it. And now right-click it. Open with Notepad. There we go. Okay, does everybody say out equals 1 if? Are these reverse canonicals or standard canonicals? Standard. So I want Mr. Flynn in his first part of the statement, the logic statement, to write out equals what? 0, because they're reverse canonicals we're talking about. Out equals 0 if on the notepad. No, not here. On your notepad, the empty one. The blank screen. There you go. Out equals 0 if, put it in big letters. If, okay, now let's just, all right, let's not worry about curly brackets right now. Let's just use words, okay? Let's just use words, not symbols, because it's going to be easier if it's in English. If what equals 0 every time. We already pinned it. There's an input that has to have a certain value all the time in order for this condition to be true. Let's go back to his canonicals, his reverse canonicals. Which input has the same value each and every time? And what is that value? Oh, so let's go back to your statement. And what I want you to do, just to keep this clear, let's put left parentheses. Left parentheses right there at the end. And then put O equal 1, right parentheses. And in all caps. Next line, indent. Okay, now, everyone look. Let's look at the reverse canonicals, okay? The first case, C and H are 0, right? The second case, C is 0, H is 1. In the third case, I'm looking at the canonicals now. Is everybody looking down at each one of those? The third case, let's look at each one. In 13, on row 13, C is 0, H is 0. Everybody see that? Line 14, C is 0, H is 1. Everybody see that? Next line, C is 1, H is 0. Everybody got that?
Yeah.
Okay. So let's go back to your note. Put C equal 0, comma, H equal 0. And then put in big letters or. All right. Next line, indent. C equal 0, comma, H equal what? That's it. Or, next line, indent. C equal 1, comma, H equal what? That's it. That's your logic statement. Now, why do you care? You can take this logic statement, and that's a form of pseudocode. What we've done is use the words and or, and it's symbolic that we're using symbols with our pseudocode, but basically you could walk into you could walk into Python, you could walk into Java. You could take these logic statement and convert it into programming statements, couldn't you? Yeah, you could. You could write software that does this. You could have the software equivalent of this logic gate design, and you could run it in software for certain applications. Like, I don't know, gaming. Like if you had a device that did a certain thing in a game, you could have like an accessory that's a physical device. Is everybody listening? Virtual reality accessories. You could have a physical device, but you could also have like a virtual device that does it in software. I hope you get where I'm going with this. Okay, so this is really important to understand, because as he modifies his HDL, he's going to be looking at this and his diagram when he does the last part of the HDL. And again, we're doing that on Monday. We are not doing it today. We're taking everybody to this place. I would appreciate just a gesture of an expression of appreciation for Eric and his courage to do this with us. And thank you, Eric. That was a very good job. And I really appreciate the way you took the truth table and you customized it for your given diagram. Those are things we typically see later on in the modules later on, right? Because people get used to those things. So what you've done is the motorcycle equivalent of you've popped a wheelie and you still have the training wheels on, right? So you're already getting ahead. Thank you very much. Is there anyone else that would like to share their diagram and walk through a truth table? We're going to pick up the pace. We'd like to do 2 or 3 more before we run out of time. Is there anyone else that would like to share their diagram and their truth table, or their diagram and just the template, and we'll do the truth table together? Do I have a volunteer for additional credit? Going once? Going twice? No one wants to grab a template and share their diagram and do the truth table together in class? Walk through it, then part of your stuff would already be done, and you'd log additional credit. Okay, and I'll also buy you lunch when I'm over on St. Thomas or here on St. Croix. You too. Anyone else? Okay. What I'd like you to do over the weekend is to complete the same process that you saw demonstrated by Mr. Flynn. And thank you again, Mr. Flynn, for your willingness to walk through as a live example, right? And on Monday, what we'll do is show how you take the logic statement and modify an HDL and create your own custom HDL and to start the process. Ultimately, when the HDL is finished, when you run, what you should see are the same results for the canonicals. So how do you test to see if your HDL works? You look at your canonicals, you put in the cases, you walk down through the inputs for the truth table, and if it matches, you've just built your first combo logic gate and you're on your way to designing digital components. And that's all it takes. So that's very powerful when you think about it. And you should think about it. All right, we're going to go ahead in the interest of time and sign off for now. And I'll stop recording. And I'll stop recording. If anyone wants to stay in place after we stop recording and you'd just like to walk through it, you and I, one-on-one, we can do that right now. I'll be here for the next 60 to 90 minutes. If anyone wants to hang out, share your screen, we just won't record. Yeah.